Welcome to Week 8, Lecture 1, Angular Momentum. So this is most of Chapter 10, Angular Momentum, Conservation of Angular Momentum, and then Precession. So angular momentum is the angular equivalent to linear momentum, and it is given by the cross product of r, the distance from the axis of rotation, and the linear momentum. We have an example here where there is a point mass rotating around the z-axis as shown. Point mass, z-axis rotating. We have the vector r and the vector of the momentum. And we can use the right-hand rule for a cross product to find the direction of the angular momentum vector. So I am going to try and do this with my left hand so that when you see it, it's a little easier to interpret. But make sure you use your right hand. So your fingers point along the direction of the r vector. So pointing out from the z-axis, and then you curl your fingers in the direction of the momentum vector, and your thumb points in the direction of the angular momentum. So this is just the right-hand rule for a cross product. Fingers in the direction of the r vector, fingers curl in the direction of the momentum vector, thumb points in the direction of the angular momentum vector. We can find some other relationships with angular momentum by taking the derivative with respect to time. And how this works for a cross product is that we end up with the derivative of the radius with respect to time. So here crossed with the momentum, and then the radius or distance crossed with the derivative of the momentum with respect to time. This dr dt is just velocity. So we end up with velocity crossed with momentum, which is mass times velocity. But a cross product, the cross product of two vectors pointing in the same direction is 0. And velocity is literally, these are the same vector. So this term goes away, it's just 0. That leaves us with the distance crossed with the time derivative of the momentum vector. And the time derivative of the momentum vector from when we learned about momentum is the net force. So the time derivative of the angular momentum is the radius or distance crossed with the net force. But again, there's more here. R crossed with the net force is the net torque. This relationship. So what we actually have, which should actually not really be surprising in the end, is that the net torque is the time derivative of the angular momentum. This is also what we found for linear momentum and force, which is why it shouldn't be too surprising. For a system of particles, we use capital L instead of a lowercase l. Sorry, I didn't specify earlier that this is lowercase l. So it's just the angular momentum of a system of particles is just the sum of each particle's angular momentum, and then the total net external torque is equal to the angular momentum of the system, or the time derivative of the angular momentum of the system. So angular momentum is analogous to linear momentum in this way. Let's say we have a system with linear momentum and another with angular momentum. So just like a particle moving and a disk spinning. An external force acts and an external torque acts on the other, on the spinning system. And we can break the external force and torque into components that are parallel to the initial linear and angular momentum and perpendicular. So the parallel components of the force here, and perpendicular, the parallel component of the torque, and perpendicular. And this application of a force and a torque will result in a change of momentum that is parallel to the force in both cases. So for example, and in both cases, you also find the results from vector addition. So let's just focus on the angular momentum one first. So here's the parallel component of the torque that changes the magnitude of the angular momentum. And then the perpendicular component of the torque changes the direction of the angular momentum. So the parallel component, we can just add that change in momentum to it because they're in the same plane, they're parallel. But then the perpendicular one, we have to do more vector addition, and that just tells us how the object or the angular momentum of the object changes direction. Just like how the linear momentum of the object would change direction. For rotation about a fixed axis, so an axis that isn't changing in relation to the object, the angular momentum is also equal to the rotational inertia times the angular velocity. So this is analogous to the linear momentum, which is the mass times the linear velocity, or the, what did we call the mass, the linear inertia? I'm not sure, I can't remember. If we plug in this equation for angular momentum, we get out Newton's second law for rotation. So we have this relationship that we established already, where the net external torque is the time derivative of the angular momentum, which is the time derivative of the rotational inertia times the angular velocity. And if we assume a constant rotational inertia, this is then the time derivative of the angular velocity. And the time derivative of the angular velocity is angular acceleration. And this gets circled all the way back to Newton's second law for rotation, which is that the net external torque is equal to the rotational inertia times the angular acceleration, or the linear analog where the net external force is equal to the mass times acceleration. And because of this, if there is no external torque acting on the system, the angular momentum is conserved. So if there is no net external torque, if it's zero, that tells us that the time derivative of the angular momentum is zero. And if the time derivative of something is zero, it just means it's constant. So the initial angular momentum equals the final angular momentum. But so this part, again, is still the same as linear momentum. But this is where there's an interesting difference from linear momentum. So let's imagine this situation. A weightlifter is sitting on a spinning stool for some reason. Initially, they hold the weight all the way out. So they hold their arms all the way out, and they move with some initial angular velocity. So initially, their arms are all the way out and they're spinning at a speed, initial speed. But then they pull their arms in and spin really fast, or their angular velocity increases. But if there's no external torques acting, and that means that angular momentum is conserved. So how is this possible? Oh yeah, I have an equation. The rotational inertia must be changing in this case. And we know this is true because when we learned about rotational inertia, we learned that the further the mass is from the axis of rotation, the harder it is to rotate, or the larger the rotational inertia. So we start with a bigger rotational inertia in this situation and a smaller angular velocity. But then when they bring the weights in, we get a smaller rotational inertia and a larger angular velocity. And now we're going to talk about precession a bit, and I want to play you a quick video demo of precession of a bicycle wheel. Okay. Okay, let's talk about what happened for a second. So it starts out, the bicycle wheel has an axle through the middle, and it's just hanging from this string rope. And then someone comes up and gets it spinning a whole bunch. And once it's spinning, they stand it up like this, and instead of falling back down like we might expect, it precesses or moves around in this circle. So we're going to look at how that happens. Okay, and looking at how this happens, we're going to break down how this works with a smaller diagram. And so this slide is just to give you a baseline for what you're looking at. So this is the diagram we're going to be using, but this is what I want you to think of is the bicycle wheel is this disc, and then we have this axle through the middle of it. Okay, so now we're going to start with our wheel at the origin of a 3D coordinate plane, which is this. So we have the z-axis, x, and y. And the wheel is rotating counterclockwise around the z-axis. We can use the right-hand rule to get the direction of the angular momentum. So in this case, when we have just an angular velocity instead of linear momentum in the distance, for just angular velocity, we do the version of the right-hand rule where we just curl our fingers in the direction of like clockwise or counterclockwise direction of the rotation, and our thumb points in the direction of the angular momentum and also the angular velocity. They are vectors that point in the same direction. So anyway, curling our fingers counterclockwise, thumb points up. Make sure you're using your right hand. So that's our angular momentum vector pointing straight up along the z-axis. Then now we can apply force to the axle like this. It's really applying a torque, so we're going to apply a force to either end. And the top force is along the positive x-axis or in the positive x direction, and the bottom is in the negative x direction. Now we have a force acting on the axle of our wheel, and we can see what torque this might cause. So again, we want to use the right-hand rule for a cross product, the one for torque. So this, we do R cross F, and R is just this like along the axle toward the force. So I'll do the top one first. So, 1 second. Okay, so fingers along the R direction, curl fingers in the direction of the force. So along the x-axis, positive x-axis for the upper part, and thumb points in the direction of the torque. So in the positive y direction in this case. And we can do the same with the force applied at the bottom. So fingers in the direction force. I'm sorry, I'm not even showing it to you. Anyway, you can also do it for the bottom, but it's the same torque. So the torque acts in the positive y direction. So we know the direction of the angular momentum, positive z direction, and the direction of the torque, positive y direction. But what does this information tell us? Well, the angular momentum vector is going to precess in the direction of the torque. So the vector will go from pointing straight up in the z-axis and tilt toward the y-axis. So it'll look like this. And it means it will start to rotate that direction. So it will tilt like this and be in between those two axes. So here is the just the vectors acting here. Let's try another one. Now our wheel is along the y-axis, as you can see. It's still rotating counterclockwise. And we also have these forces along the x-axis applied to the axle. So the right-hand rule tells us the angular momentum vector points along the positive y-axis. So again, because that is just the curling the fingers in the direction of the rotation, thumb points in the direction of the angular momentum. And then we have these two forces applied in the x direction on the axle. So right-hand rule for this is fingers in the direction of the of R, and then curl in the direction of the force, and our torque points down or in the negative z direction. So there's our torque. And so this tells us what we just learned is that when there's a torque acting and there's angular momentum, the angular momentum is going to precess in the direction that the torque is acting. So the torque is changing the direction of the angular momentum. So this time it will tilt down because the vector is here on the positive y, and the torque is in the negative z. So it's going to precess down, which is what this looks like here. So you're going to practice this in the self-check, and I think maybe in the application. But please reach out if you have questions about how to do the right-hand rule. I mean, you can definitely Google it. There's tons of physics resources on right-hand rules in physics. But also I was trying to do this with my left hand so that it looks clearer for you, but that also is challenging. So please let me know if you're confused. Okay, last thing is I just want to end with this table relating translational and rotational quantities from velocity all the way to momentum. So velocity, acceleration, mass and rotational inertia, torque and force, Newton's second law for both, and we just derived this in another way. What is required for equilibrium, angular and linear momentum, total or angular and linear momentum for a system, how the momentum is related to the net torque and net force, and then again another version of Newton's second law, and then conservation of angular and linear momentum. So this is a good table to refer to. It has both the linear relationships and the angular one, rotational one. Okay, that is all for this lecture.